Hi, this is A Trip to the Moon, Part 2. In this part, we'll look at a transfer orbit to the Mun. The planet Kerbin has two moons, and the nearest is called the Mun. The Mun orbits above Kerbin at an altitude of 11,400 kilometers from the surface of Kerbin. Because we launched our rocket from the equator with a heading of 90 degrees due east, our initial orbit is directly above Kerbin's equator, and this means our orbital inclination is at 0 degrees. Fortunately, the orbit of the Mun is also at 0 degrees inclination, and therefore reaching the Mun is only about increasing our altitude and correctly timing the intercept. So here's the planet Kerbin, and here's our rocket orbiting around at 100 kilometers altitude. It's orbiting around in a circular orbit. And out here is the Mun. So we're orbiting at 0 degrees inclination, and the Mun is also orbiting around Kerbin at 0 degrees inclination. Over here is another moon called Minmus, which we won't try to intercept with that. Our target will be the Mun. Now I clicked through that pretty quick, and I missed that there was some useful and relevant information there on the screen. For example, we can see as I hover the mouse over the rocket here that the rocket that we're flying is this Kerbal X. Its velocity is 2246.1 meters per second and an altitude of 100,000 meters, 100,046 meters, so roughly 100,000 meters. So that is the circular orbit that the rocket is in around Kerbin. And if we zoom out here to the Mun, we can also see that the Mun is orbiting at 542.5 meters per second at an altitude of 11,400,000 meters. So these will be relevant to us as we progress further along in this analysis. In fact, what we'll try to do is figure out how do we get from this orbit, the circular orbit around Kerbin, all the way out here to the Mun. That's the real objective of this video. Here's one place where our Kerbal Space Program really simplifies our work. In real life, the Earth is tilted relative to its orbital plane, called the ecliptic, and the Moon's orbit is inclined relative to the ecliptic and also to Earth's equatorial plane. You can see this line here, the ecliptic plane. This is the plane of the orbit of the Earth around the Sun, and Earth is tilted relative to that plane, and the Moon is orbiting around the Earth in a plane that is tilted to the ecliptic plane, and of course tilted to the equatorial plane. So all of these different angles between these planes is much more complicated in real life than what we have to deal with in Kerbal Space Program. In the game KSP, the Kerbin Mun system is much simpler. The Mun orbits around Kerbin at 0 degrees inclination, directly in line with both Kerbin's equatorial plane and orbital plane. The distance from the center of Kerbin to the center of the Mun is exactly 12,000 kilometers. Further, because Kerbin has a radius of 600 kilometers, this is why we've concluded the Mun is orbiting at an altitude of 11,400 kilometers. That's the altitude above the surface of Kerbin. So here's Kerbin with a 600 kilometer radius, and the distance from the center of Kerbin to the center of the Mun, that's 12,000 kilometers. But because Kerbin has a 600 kilometer radius, actually from the surface of Kerbin to the Mun, that's 11,400 kilometers. So here in part 2, we'll compute the elliptical transfer orbit required to reach the Mun from Kerbin. Maybe first I'll back up and just do a quick review of some basic terminology concerning elliptical orbits. So we talk about an equatorial plane. We're talking about the plane that contains the equator of the primary body that we're orbiting. And so we might be orbiting at an inclination in an orbital plane that is tilted to the equatorial plane, for example. So when we talk about the inclination, we're talking about this angle here between some reference plane, like for example the equatorial plane, and the actual orbital plane, the plane in which the orbit is a two-dimensional ellipse. So all orbits are ellipses, and even specifically a circular orbit is an example of a specific ellipse where both foci are at the same point in the center. So in the diagram below, the points F1 and F2 are two foci of the ellipse. And we talk about the semi-major axis, we're talking about the length of, or actually half of the length of the major axis. So the major axis is the larger axis. This axis is the major axis of the ellipse. This is the minor axis, and they intersect, of course, at the center of the ellipse. So we've got a semi-major axis that is half of the major axis, and of course a semi-minor axis. And those are some fundamental parameters of the ellipse. Also, a very important basic parameter of the ellipse is its eccentricity. So the eccentricity is the distance from the center to either focus divided by the length of the semi-major axis. So once we have an elliptical orbit, it can be written in a polar form with this type of an equation here. This is the polar form of an ellipse. And A represents the length of the semi-major axis. E represents the eccentricity. It's a measure of how oval the shape is. And when we're talking about orbits, we'll often refer to this angle theta that's called the true anomaly. It's the angle measured from the primary focus from the point of periapsis, the closest approach to the focus, to the current position in the orbit. Anomaly is a word that sort of means something wrong or error, but in this case what happened is it comes from the history of the discovery of elliptical orbits, how they're not perfectly circular, and so that was a discovery that they aren't exactly circular, and so there's a deviation from circular. That's where the term anomaly came from in this context. Now the primary body, either Earth or Kerbin in this case, has its center at one focus of the ellipse. So that's right here. So this is the radius of the Earth in this diagram. There is empty space at the other focus, which would be somewhere maybe over here. In the diagram here, RP is the radius of periapsis. That is the closest approach to the primary. So here's RP, that's the radius of periapsis. This would be the point of periapsis when we're closest to the focus of the ellipse, or the center of the primary body. And RA is the radius of apoapsis. That's the farthest distance. RA is the distance from the center of the primary body, or the primary focus, to the farthest point on the orbit. So that's the radius of apoapsis. The radius of apoapsis is this distance from here out to there. We also have periapsis and apoapsis altitudes indicated in the diagram. So HP would be like height at periapsis or altitude at periapsis. That's the distance to the surface of the planet. And this HA would be the apoapsis height or altitude. That's the distance from the surface to the point of apoapsis, the farthest from the primary body. Velocities at periapsis and apoapsis are indicated also in this diagram. So the velocity is this direction, this vector that indicates the direction of travel, and it is tangent to the curve. So this would be the velocity at periapsis, going in this direction if the satellite or rocket is orbiting around in this direction. So this is a vector indicating the velocity at apoapsis, and it's drawn a little bit smaller because it's actually slower generally at the apoapsis than it is at the periapsis. The semi-major axis is A, so that's from the center to one end of the major axis. So it's the same distance from the center to the apoapsis as from the center to the periapsis. There's also just the velocity at any particular point in the orbit given by this vector v, so it's tangent to the orbital path. And there's a flight path angle indicated here, phi, and that's the angle between velocity and the perpendicular to the radial vector. So the radial vector is this guy. This is perpendicular to the radial vector. It's the same as tangent to the surface. So it's like the horizon, but drawn at the local point of the orbit. So the angle between velocity and that horizon, that's the flight path angle, phi. We'll get to that. I think it's part 3 where I was planning to talk about calculating that flight path angle. That's a really neat topic. Okay, here in GeoGebra, I have a graph, a diagram of the planet Kerbin with a radius of 600 kilometers and 100 kilometers from the surface. We've got an orbit, a circular orbit, and this point right here, P, is where our rocket is orbiting right now, currently in a circular orbit around the planet. Now, if we want to reach the Mun, let's zoom out. The Mun is orbiting out here in a circular orbit at 12,000 kilometers from the center of Kerbin. So what we'll need to do is increase our velocity to create an elliptical orbit. And so you can see as I change this focus so that we have now 2 foci, the effect is higher velocity is taking the rocket further away from Kerbin, but in the gravity field, eventually, unless it's enough to escape the gravity of Kerbin, the gravity is going to bring it back in this elliptical orbit. So we're looking for creating enough initial velocity there so that we create this elliptical orbit that reaches all the way out to the Mun. Something like that. So we'll try to figure out what exactly is this orbit, this elliptical orbit that will take us out there. Now, of course, we also have to be aware of the fact that the Mun is moving around the planet, so we want to time the intercept so that we do this burn at the right time to intercept the Mun. But that's the thing that we'll be studying right now, is to try to figure out what is the equation of this elliptical transfer orbit. So this diagram shown below is a view from above the orbital plane of the rocket. So the rocket would begin here at the closest point to the planet Kerbin at an altitude of 100 kilometers, and that's the periapsis of the transfer orbit. The transfer orbit would take us on this path out eventually to intercept with the Mun, and that would be the apoapsis of the transfer orbit because that would be the furthest point from Kerbin. And we've established that the Mun is 11,400 kilometers above the surface. A total distance from the, its total distance is 12,000 kilometers from the center of its orbit, from the center of Kerbin. So the Mun orbits around in a big circle, 12,000 kilometers from the center of Kerbin, or 11,400 from the surface of Kerbin. So the radius of Kerbin is 600 kilometers. The radius of the Mun orbit is that 11,400 plus 600. That gives us this 12,000 kilometer radius of the circular orbit of the Mun. And so to describe the ellipse of the transfer orbit, 2 important values are the semi-major axis A and the eccentricity E, and we can now calculate what those are. The apoapsis of the transfer orbit is 11,400 plus 600, giving me 12,000 kilometers. Because my transfer orbit has this as its primary focus, the center of Kerbin. So the apoapsis is the farthest distance in our orbit from the focus, so that's the 11,000 plus 11,400 plus the 600. That's a 12,000 kilometer apoapsis, and the periapsis of this transfer orbit is the distance from the primary focus of the orbit to the periapsis, which is 600 plus 100. That's 700 kilometers. And so the semi-major axis of the transfer orbit is half of this total major axis. And a total major axis is all of these values added together, 11,400 plus the 600 for the radius, plus another 600 for the radius to get the entire diameter of Kerbin, plus this 100 kilometer altitude above the surface. So we're getting 12,000 kilometers on one side of the focus, 700 kilometers on the other side of the focus, 12,700 kilometers total for the length of the major axis. A is half of the major axis, so A is 12,700 divided by 2, 6,350 kilometers. That is the semi-major axis of the elliptical transfer orbit that we're calculating. Now to compute the eccentricity for this orbit, I know that the semi-major axis is 6,350 kilometers. So I'll draw a major axis and put the center in the middle of that major axis. And from the center to the Mun, the center of the Mun actually, that's 6,350 kilometers. That's half of the major axis. And the other half goes from the center to the periapsis. Now I already know that the planet Kerbin has a radius of 600, therefore a diameter of 1,200 kilometers. So if I add 600 plus this 100 kilometer altitude of periapsis above the surface, this is 1,300 kilometers already included on this half of the major axis. So if I take the 6,350 kilometer semi-major axis and subtract the 1,300 kilometers that are already included in this part of the diagram, that leaves me with 5,050 kilometers that I know would cover the distance from the center of the orbit to the surface of the planet on this inside of the this inside surface. So now I can figure out what is the distance from the center to the focus of the orbit. It's actually the 5,050 plus 600. 5,050 plus 600, that's the value that we could call c, the distance from the center to the focus, divided by the semi-major axis, 6,350. 5650 divided by 6,350, that gives me 0.8898. That is the eccentricity. That's a pretty high eccentricity. For an ellipse, eccentricity is between 0 and 1. So if you actually hit 1, you have a parabola. If you're actually a 0 eccentricity, that's a perfect circle. So ellipses are between 0 and 1, and this is closer to 1 than it is to 0. It's pretty elliptical, pretty highly elliptical orbit. Let's take a look at the graph. So let's start with a radius 600 for the planet Kerbin. So there's the planet Kerbin. We could make another circle with a radius 670. That's the altitude of the atmosphere. R equals 700. That's our circular orbit. Now we've just computed the semi-major axis is 6,350, and with an eccentricity of 0.8898, let's type this in as our polar equation for the orbit, the transfer orbit. It looks something like this. So let's go 6,350, 1 minus 0.8898, and you have to square that. Divide by 1 plus the eccentricity, cosine, and you could just type theta and it'll figure out what you mean. And so there is, this purple curve is the transfer orbit reaching out exactly to an apoapsis at 12,000 kilometers from the center of the planet. Okay, so that's what I've done here in Desmos, a 600 kilometer radius planet with a 700 kilometer radius circular orbit. I have a transfer orbit with a semi-major axis 6,350 and eccentricity 0.8898. So that is the transfer orbit. I've labeled the center 5650. Remember, I know the center is at 5650 because if my primary focus is at the origin in the graph, this is a distance of 5650 from 0, 0 out to the center. So by graphing a polar equation in this form, it puts the focus, the primary focus of the ellipse at the origin. So these are circles centered at the origin. Here I have circles centered at the origin, which is where I have the focus. And this ellipse has its focus, primary focus, also at the origin. And so by graphing this point 5650, that's the distance from the center to the focus. I've identified where the center of the ellipse is, and I've also identified where the apoapsis and periapsis are, and the focus is there at the point 0, 0. Calculating speed during an elliptical orbit is now more complicated than it was for the circular orbit. Except exactly at periapsis and apoapsis, the gravitational acceleration on the rocket is no longer perpendicular to the velocity, and therefore gravity will speed up or slow down the rocket depending on its direction. So to calculate speed, we can use the principle of conservation of energy, which says that the sum of the potential and kinetic energy during the orbit will remain constant. As the rocket gets further from the planet, its potential energy increases and its kinetic energy and thus speed will drop, and conversely, as the rocket approaches the planet, its potential energy drops and its speed will increase. So the conservation of energy is the principle that this kinetic and potential energy sum will remain constant. And so this is the kinetic energy here, this is potential energy, and this is a value that represents what that constant value would be, the sum of the total energy. Now the first thing that we could do here is recognize that the mass of the orbiting body, this little m, this will cancel out in each of these terms and get this equation here. So what I could do with this equation now is solve for v to determine the speed at any particular point r, depending. I basically calculate it from the potential energy. So solving for v squared, just bring this term over to the other side. Multiply both sides by 2. Now there's a gm factor in both terms, so I'll factor that out. Gm, I'll just write that as mu. Mu is this gravitational parameter that I referred to before. So if you want to solve for velocity, you've got two different values, plus or minus, just indicating one direction or the other. And this is what's called the vis-viva equation. It tells you the speed, so it's not really technically the velocity, it's really the speed, because it's just a scalar value, just a number. But if you know the semi-major axis and you know the position, the radial position, how far you are, the distance from the focus of the orbit, if you know that value of r, and the gravitational parameter for the primary body you're orbiting, well, you can calculate the speed that way. So let's compute the initial speed of this transfer orbit at the periapsis to find the required velocity to reach an apoapsis of the orbit exactly at the Mun. So remember, my semi-major axis was 6350. That's 6,350,000 meters. And so the radius at periapsis is actually exactly the 700 kilometers or 700,000 meters. So with a radius at periapsis of 700,000 meters and a semi-major axis of 6,350,000 meters, and this particular gravitational parameter, plugging that into a calculator, I get 3,087 meters per second is the speed that you would need at periapsis, or you would have at periapsis on that transfer orbit. So if I was in a circular orbit with an initial speed of 2246, and I wanted to increase to reach the Mun, I would have to increase my speed to 3,087 meters per second. So that's an increase of 841 meters per second. That's the delta V, the change in velocity that's required to produce exactly that transfer orbit to reach an apoapsis at 12,000 kilometers from the center of Kerbin, from the focus. Now recall part 1, we had computed an escape velocity of 3,176 meters per second to escape Kerbin's gravity from an altitude of 100 kilometers, and that would require a delta V of 930 meters per second. So we can now see this is more than the delta V required to reach the Mun, which was about 841. Is it 841 meters per second to reach the Mun? That's less than the delta V required to escape the gravity of Kerbin. And we conclude that at the Mun, we would still be in the gravitational field of Kerbin. And this does make sense, of course. This is the reason the Mun is orbiting about Kerbin. It is close enough to Kerbin to be within Kerbin's sphere of influence. And at its orbital speed, it is in a bound orbit about Kerbin. When we reach close enough to the Mun, though, within a 2,429.6 kilometer radius sphere of influence of the Mun will become the dominant gravitational body, entirely determining the orbit of our rocket. So that isn't to say that we will necessarily get pulled in and crash into the Mun just because we've entered into that sphere of influence around the Mun. We could be traveling such that, like a skateboarder along a curved wall, we just pass through the sphere of influence with our path bent by the gravitational pull of the Mun, after which we might leave the Mun's sphere of influence to once again return into the sphere of influence of Kerbin and have our orbit determined and dominated by the gravitational influence of Kerbin. So to intercept and then orbit the Mun, we'll need to take into consideration how fast the Mun orbits around Kerbin and how long it will take us to get there. And we'll look at that later in part 3. So here I've got Kerbin with a radius of 600 kilometers and a 700 kilometer altitude circular orbit, and the orbit of the transfer orbit that's going to reach out to the Mun. And this is a graph of the size of the Mun, 200 kilometer radius for the Mun. So this equation right here produces the circle that is the Mun, and so I've got that in rectangular coordinates. I've got polar coordinates for Kerbin and the circular orbit. Now this much larger circle, this is the sphere of influence for the planet Kerbin. That's the circle around which anything in that circle is dominated by the gravity of Kerbin. So that's much bigger. I have to zoom out to look at a much bigger circle around Kerbin. Anything inside that circle, Kerbin is the dominating gravitational body. That any other object is going to be is going to orbit about this. This will be the primary body, Kerbin. So the Mun is definitely well within the sphere of influence of Kerbin. But the Mun also has its own sphere of influence, which is a 2,429.6 roughly kilometer sphere of influence around the Mun. So if we get close enough to the Mun, then actually we'll enter into the sphere of influence of the Mun, and then the Mun will determine the orbit. So you can see that sphere right there. That's the radius there, 2,429.6, roughly the size of the sphere of influence of the Mun. So as we travel along this elliptical orbit about right about here, the path will no longer be influenced by Kerbin. Instead, it'll be influenced by the Mun. Let's calculate how fast we would be traveling at the apoapsis of the transfer orbit. So at the apoapsis, the position we can compute by r by the polar equation for the ellipse, and of course I know that it's 12,000 kilometers, but just it's kind of nice to see confirming that if you put 180 degrees for the mean anomaly, you're exactly at the apoapsis. And so cosine of 180, yeah, that's -1. That gives me this negative here. This is a difference of squares, and so this 1 minus 0.8898 will cancel with the 1 minus 0.8898 and leave this one factor here, 1 plus 0.8898 times the 6350. Yep, that gives me 12,000 kilometers. So we know that at the apoapsis, the R value is 12,000, and so actually it's 12,000 kilometers, which means I actually need to use 12 million meters for the position in this formula from the vis-viva equation to get the velocity. So we know the R value, we know the semi-major axis in meters, and so putting that into a calculator, you're going to get 180 meters per second for the speed at apoapsis. Now this is the speed we would experience at the apoapsis of the transfer orbit, assuming the Mun was not there. We may not exactly reach this speed because as we approach the Mun, we will encounter its gravitational sphere of influence. And if we time the encounter correctly as we approach the Mun, its sphere of influence will dominate our orbit and affect our speed before we reach the transfer orbit apoapsis. The Mun orbits in a circular orbit about Kerbin at about 543 meters per second. And this is the required orbital speed for a circular orbit at the Mun's distance from Kerbin. And if we increased our rocket to that speed at that altitude and headed perpendicular to the pull of gravity, we would achieve the same orbit as the Mun around Kerbin. But since we're traveling slower, much slower, 180 meters per second, we're traveling much slower than the required speed to maintain a circular orbit at that particular altitude, well, the gravity of Kerbin will just pull us back on the elliptical transfer orbit back toward Kerbin. So instead, if we time the intercept correctly and reach the Mun's sphere of influence, at that point, we'll attempt another maneuver to enter into an orbit around the Mun. Of use in the next part of the series, in part 3, will be the period of the orbit. We can use one of Kepler's laws, which states that the square of the orbital period is proportional to the cube of the semi-major axis to compute the period of the elliptical orbit. So this relationship is so amazing and beautiful that when Kepler discovered it, he referred to this relationship as the harmony of the spheres. So using Kepler's law and solving for the period t, we know that the semi-major axis in this case was 6,350 kilometers, or 6,350,000 meters. So the semi-major axis cubed, and the gravitational parameter is 3.53 times 10 to the 12. That gives us about 53,512 seconds, about 14.86 hours. We will need that in part 3 when we try to intercept the Mun. We'll need to know actually how long it takes us to complete this orbit, or actually specifically to get halfway through the orbit to the apoapsis. Finally, so far in part 2 of this series, we haven't done much calculus. So let's finish with one calculus question. Compute the circumference of the elliptical transfer orbit. Interestingly, it's impossible to find the exact circumference or perimeter of an ellipse. We can only find approximations, and so here we'll use a calculator to find a numerical value for the required integral. So the distance our rocket would travel if it completed the entire elliptical orbit is given by this formula. In this formula, E is the eccentricity and A is the semi-major axis. So in this particular example, with a semi-major axis of 6,350 kilometers and an eccentricity of 0.8898, finding the perimeter or circumference of the ellipse, we'll have to use a calculator. This is something that you cannot find an exact antiderivative for, so we'll not be able to ever find an exact value for it. One thing is to use a calculator computer to give a decimal approximation, which is what I've done here, about 1.184. So multiplying all that together, this is about 3,073 kilometers for the entire distance around this ellipse. That's about 30 million meters. So half of that is 15,368,000 meters, or about 15,368 kilometers. This seems reasonable considering that the straight line distance from the periapsis to the apoapsis was 12,700 kilometers. Let's go back in the game simulation and see if our transfer orbit looks right. We'll need to add a maneuver to fire the rocket prograde, meaning we'll increase our velocity in the direction we're currently headed. We can do that here, add a maneuver. So we calculated a required delta V of 841 meters per second to reach the Mun. So this is version 1.7 of the game, so we can enter that precisely at the bottom of the screen. Okay, so now we see the projected transfer orbit. Our lunar transfer orbit, it looks good, taking us to the Moon's orbit. The only trouble is timing that rocket burn to actually intercept the Mun. I'll save that for part 3, and we'll check a lot of these calculations from this part that we've made here when we get to part 3.